Hi, everybody. Welcome back to the Feynman technique. Today, my goal is to develop a closed form expression for both these integrals. All right, so where are we going to start? Well, first, let's start like this. Let's notice that e to the ibx is equal to cosine of bx plus I sine of bx. All right, so let's use that like this. We can call this integral now the real part of this, e to the ibx, real part. And this one will just be the imaginary part of the same thing. This is just e to the ibx. Hope you're following along so far. All right, so next what we should do is combine our exponents. So this is going to be, let's see, ibx here. Hope you see what I'm doing here. I'm just combining the exponents. We have the common base, so we can just add the exponents. ibx. And then let's go ahead and factor out a negative x on both of them. Negative x, that's going to give us negative ib plus a. All right. And then, of course, I'll put the a over to the other side. And let's go ahead and put that in front of the x. All right. Now, the same thing's going to happen over here, so I'm just going to go ahead and copy that right there. All right, so, well, this is kind of a form that I recognize. Let's develop it, though. Let's say we have a function of t equal to the integral from 0 to infinity of e to the negative tx dx. That is going to be exactly 1 over t. Okay, now let's go ahead and take a derivative on both sides. All right, so taking a derivative of, let's see, of taking the derivative of this integral, we'll use the Leibniz rule for differentiation under the integral sign, which says we can take the derivative with respect to t directly by taking the partial with respect to t of the integrand and leaving the rest alone. So what we'll get is a negative x e to the negative tx. Partial with respect to t of e to the negative tx is negative x e to the negative tx. All right, and then we'll go ahead and bring that negative sign outside. And on this side, we're just going to end up with a negative 1 over t squared. All right, let's take another derivative. So f double prime of t, well, let's see what's going to happen here. We're going to recover another negative sign, which is going to cancel that. And then we're going to recover another factor of x. And over here, we're going to multiply, we're going to cancel this negative because we'll recover another negative. And then it's going to be 2. We will also recover a factor of 2. All right, let's do one more derivative just to see the pattern here. So we have, oh, I better make this a little bit smaller. Okay. Let's see. There we go. All right, I hope you guys can all still read that. All right, so where was I? I was taking another derivative. So we have f triple prime. All right, over here, for this one, we'll again recover a negative sign and another factor of x. And on, oh, I'm sorry. Over here, this was supposed to be a 3. Yeah. And over here, we'll recover a negative to another factor, a factor of 3, and we will advance our t by 1. So this is enough to see the pattern here. All right, so the pattern is this. if we take n derivatives of our function of t, we get -1 to the n times the integral from 0 to infinity of x to the n e to the negative tx dx. We recover we will get a -1 to the n over here. Now notice, every time we take a derivative, we're adding the next integer in this sequence to its product. So basically what that means is we just have n factorial. And this index right here, this 4, this power on t is always going to match our whatever derivative we're on plus 1. So we can say t to the n plus 1. All right, so now we have f, the nth derivative of our function of t is equal to this. Okay. Well, and it's also equal to this. Let's clean this up a little bit. We don't need the -1 to the n on both sides of that equation, do we? No. So we can just say this. We'll divide both sides by -1 to the n. And now we can say this. Now let's take a look at our integrals right here. We pretty much have this form where our t is a minus ib. All right. So now we can say that our original integral I is equal to the real part of the nth derivative of our function evaluated at a minus bi, right? We can say that. And j is equal to, well, it's just going to be the imaginary part of that same thing. All right, let me make sure I did everything right. Yeah, that's right. Okay. So that means I is equal to the real part of our nth derivative of our function at a minus bi. Well, don't forget, this is the nth derivative of our function evaluated at t. So what we do is we just plug in a minus bi for t. A minus bi. All right. And that's going to give us j is equal to the imaginary part of that same thing. Okay. So now what? Well, now we basically have it. Now we just need to take the real and imaginary parts of that. Okay, so I'm thinking of multiplying the top and the bottom of both of these by a plus bi to the n plus 1. So let's do that. So we're going to multiply the top and the bottom by a plus bi to the n plus 1. And then our j will just be the imaginary part of this same thing. All right, great. Okay, so now let's take care of the bottom part of both of these. Let's see, that's going to give us a squared plus b squared to the n plus 1. All right. I hope you guys are following along. All right, so now the only part that's causing me a problem right now is this a plus bi to the n plus 1. So let's work out a plus bi. So any complex number in that form is equal to the magnitude r times e to the I argument. Okay, but I don't like writing it like that. Let's see, r, the magnitude of that. Don't forget, this point creates a triangle in the complex plane. The distance between the origin and the point a plus bi in the complex plane is the magnitude. That's just going to give us square root of a squared plus b squared by the Pythagorean theorem. Now, the argument is the angle that this thing makes with the origin. Okay, so, well, if we have, basically this is going to make a triangle with opposite side B and adjacent side A. So we can say that our argument is just the arctangent of B over A. So we have e to the I arctangent B over A. Okay. Let's see. We can do a little bit better than this, I think. Yeah. Well, we need to raise both sides to the n plus 1 power, don't we? To the n plus 1 power. And that's going to equal this side to the n plus 1 power. All right. Well, that's just going to equal, let's see. This is a product, so we can just raise both parts of that product to the n plus 1 power individually. All right. So that's going to be this. All right. Well, this is a squared plus b squared to the 1/2. So we can just say this is a squared plus b squared to the n plus 1 over 2. All right. And this, we can just distribute this n plus 1 inside using the properties of exponents. So we just have I n plus 1. Okay. Now let's go a little bit further and say that a plus bi to the n plus 1 power. And let's actually split this up. Let's use Euler's formula on this. So this is going to be cosine of something plus I sine of something, where our something is this thing after the I here. Okay. And now we're done, because let's just plug this in. So I is equal to this and j is equal to this, but now we have what a plus bi to the n plus 1 is. It's this. All right. So let's copy this and just paste it wherever we see a plus bi to the n plus 1. Now, this is going to require, you probably won't be able to see the entire formula on your screen here, but don't worry, I'm going to clean it up. All right. So don't forget, right here, we're just taking the real part, right? So anything that's imaginary is just going to go away. That happens to be this. So we can just get rid of that and get rid of that real part right there. All right. Now you'll notice that, well, let's take care of this part over here now that you can see it. So we're taking the imaginary part. So we get rid of the I, we get rid of that, and we get rid of that and this, and we no longer need the imaginary operator there. Okay, so yeah, we're done. We can clean it up a little bit though. Let's go ahead, and you'll notice we have powers of a squared plus b squared in the numerator and denominator. So what I'm going to do is I'm going to put a parentheses around here, and then I'm just going to subtract n and subtract 1. Okay, and now we don't need this part. And cleaning this up, this is 2n over 2. This is 2 over 2. So we can just go ahead and subtract 2n and then subtract 2. And now we don't need this. Let's see. 1 minus 2 is negative 1. N minus 2n is just negative n. And then we factor out the negative sign, and we have an n plus 1 over 2. And that should be basically the exact same thing for our j, except it's going to be sine instead of cosine. So I'll just copy that over there. The algebra would work out the exact same way. And now we have sine. All right, let's see if this worked. All right, so what were our original integrals? I and j were this. So let's see if these things, let's see if we got the right answer. All right, so let's compare our original integral I, and then I'll just put in some arbitrary values for n, a, and b, and let's see if it matches our expression for I. It should. Yeah, matches pretty well. Let's just take some different values. Yeah, it's holding together quite nicely there. Yeah. All right. And now let's see if it holds for the sine version. Should just replace this with a sine. Yeah. Yeah. All right, guys, that's it. Two integrals in one today. So we solved these two integrals, and they are equal to that and that respectively. All right, guys, I hope you enjoyed that, and we'll see you next time.